Okay, so we're going to do chapter 14. I'm going to make this into small videos. I have done this once before, but these are apparently ones that I didn't create jar files for, so I just have to do it again. Don't really want to have to, but that's the way it goes. Okay, so in chapter 13 we talked about waves. Well, we talked about vibrations, sinusoidal variation of position with respect to time for spring mass systems and pendulum systems. Then we talked about waves on a string, mostly. The other kinds of waves we have are sound waves, and we have light waves. We talked light waves briefly, but chapter 14 is about sound. And so sound is just like any other wave. There is a disturbance, which is some energy input to a medium, which in this case is air. And that disturbance is propagated through the medium, used through waves. So the most fundamental way of producing a wave of a exact frequency, of a given frequency, is to use a tuning fork. So if you've ever used those, you hit them against some surface, and these forks of the tuning fork vibrate, and that vibration makes the air close to the tuning fork also let me just show you on the next page. What it does is it causes the air to compress locally and then to expand locally, and you get these local areas of higher pressure and lower pressure. Now, they're very small variations relative to the actual air pressure that we're seeing. So the pressure variations are small, but because they are sinusoidally varying, they are transmitted as waves through the space. Let's see if I can actually get this thing to do something. No, okay, that didn't work. So let's go back. Now, a tuning fork gives you a single frequency, and it's because you can only get the fundamental frequency of the tuning fork. With strings and with other things, you can get harmonics, but in this case, you just get a simple sine wave. We'll show that in class when we do a lab. So you get these a succession of compressions where the pressure is higher. That's the peak. And so what this graph represents is the pressure, again, through space. So you've got a variation in pressure through space where it's high here, low here, high here. You can also look at a given time. So for a given time, the pressure will increase and then it will decrease as these waves pass a given point in time. And because of the way things vibrate, you get a sinusoidally varying pressure, and that energy, due to the compression and rarefaction of the air, transmit through the air to something like your ear. And normally sound waves that we can hear are in the range of 20 hertz to 20,000 hertz. Now as you get older, you're able to hear less of the higher frequency noises, sounds. There's also sound waves that we can't hear, infrasonic waves. Those are below 20 hertz. And you can have sound waves transmitted through the earth, or whales, things like that. Maybe elephants might do really low frequencies, and then above the audible range, and we'll say above 20,000 hertz. So things like bats or ultrasonic sensors to look for distance use higher frequencies above the audible range, so we can't hear them, but they still have some use. And a couple of applications of waves besides just listening is you have an ultrasound machine. So what happens is you send sound waves of high frequency. They go in through the body, and then they're reflected back. And by analyzing those reflected waves, you can see something like a baby or a tumor. You can also use ultrasonics to measure flow rate. That's how many pounds per minute or gallons per minute are flowing through a pipe. The advantage of an ultrasonic flow meter is you don't have to have anything inside the pipe. Actually, the pipe's right here. So what happens is that you can determine how much flow is going through the pipe without actually cutting into the pipe or doing any kind of modification to the pipe. Okay, so that's kind of the introduction to sound. Okay, so now let's talk about the intensity of sound. So sound, there's intensity and there's sound level intensity. So waves are ways of transmitting energy. So it makes sense that the sound level intensity, which we use the symbol I for, capital I, is in units of watts per meter squared, because power is watts. Now, why is the denominator in meters squared? We'll explain that in a second. Now, power, remember, is energy per unit time. Energy has units of joules, so we have joules per second for power, and we define that 1 joule per second is a watt. Now, there's intensity level, which is different than sound intensity level. So intensity level is measured in decibels. So there's a conversion from sound intensity to intensity level or decibel level, which we'll explain here in a second. So the question is, why do we have watts per meter squared? Well, if you have a source of sound, it's going to be a speaker or an explosion or something like that, or whatever it is, a car. And that energy is transmitted out as a wave in 3 dimensions. So it's not a 2-dimensional wave, but it's a 3-dimensional wave. So you can think of these spheres as being wave fronts. Well, the energy that's transmitted here in watts, it goes out, and as it goes out away from this source, its intensity, sound intensity level gets less because the amount of energy per unit area decreases. The further you are away, the larger the area is, and the less the sound appears to a person. So the surface area of a sphere is 4 pi r squared. So that's the reason that its intensity is the energy per unit area, and that's what we sense. We don't sense the actual energy transmitted from the source. It's what the energy per unit area is. So we talk about speakers or amplifiers. They have a certain power level. That's what they're generating at the source, but what we're hearing at different distances is this 60 watts divided by the corresponding surface area. So let's give an example here. So at 10 meters from the source, the sound source, the intensity is 0.001 watts per meter squared. What is the sound intensity level at 20 meters? Well, because we have the same energy over the sphere, but the sphere area is larger, what you do is you have that the ratio of intensities is equal to the ratio of the radius, the radii. And I think I've got that. Yeah, okay. But it's inversely proportional to the area because it's watts per meter squared. It's power per unit area. So we have the ratio of the intensities is the reciprocal of the ratio of the radii squared. The squared comes from the fact that the radius is squared to get the area, and the fact it's inversed is because the units are watts per meter squared. So to calculate the sound intensity level at 20 meters, you take the sound intensity level at 10 meters and multiply by the ratio of the radii. So the radii of this power sound intensity level is 10 meters, and at 20 meters you put that in the denominator, and so at twice the distance the actual sound intensity level is going to be 1/4 So the sound intensity level at 20 meters, or 0.2 in space, is 0.00025, which is a quarter of that. Okay. So that's how you work with intensities. It's a function of the distance. Now, but the ear doesn't perceive sound intensity level. What it presents, it perceives sound is in a decibel scale, which is a logarithmic scale. So it turns out that a 10 decibel change in sound, or in intensity level or decibel level, is perceived by the humans approximately double in loudness. So if you go from 70 decibels to 80 decibels, 80 decibel sound, 80 decibel intensity level sounds twice as loud as the 70 decibel level. Likewise, if you go from 80 decibels to 90 decibels, this sounds twice as loud, perception-wise. So the equation to convert from sound intensity level to decibels, or intensity level, is this. You take 10 times the logarithm to the base 10 of the ratio of the sound intensity level to this reference. The reference is, we call that I sub 0. It's 1 times 10 to the minus 12 watts per meter squared. This sound intensity level is pretty much the minimum sound level that people can hear. So this number is going to be greater than 1, and it could be much greater than 1. But then you take the logarithm of that number to the base 10, and you take the ratio. So if the sound intensity were actually equal to I0, you get a ratio of 1. The logarithm of 1 to any base is 0. So you get 0 times 10, which would be 0. So 0 decibels is going to be the limit on hearing sound. Okay. So I think I have more to say about that than what's given. So let's just do a simple calculation. So let's say the sound intensity is 3.4 times 10 to the negative 5th watts per meter squared. So what is the decibel equivalent? So the decibel equivalent is going to be 10 log base 10 of 3.4 times 10 to the minus 5 watts per meter squared divided by 1.0 times 10 to the minus 12 watts per meter squared. And if you plug that into your calculator, you get 10 times, and you do the log, log, not ln, of 3.4 e to the minus 5 divided by 1 e to the minus 12, and you get 75.3 decibels. And likewise, you can go the other direction. If I said B equals 85 decibels, then, so 85 is equal to 10 log to the base 10 of I divided by 1 times 10 to the minus 12 watts per meter squared. So first thing you do is you divide both sides by 10. So you get 8.5 equals log to the base 10 of I, unknown, 1 times 10 to the minus 12 watts per meter squared. So then you take 10 to the 8.5 power is equal to 10 to the log base 10. So those are inverse functions of each other. So you would be able to remove the log. So 10 to the 8.5 power is 3.16 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 10 to the 8th. Then you multiply both sides by 1 times 10 to the minus 12th, and you get the answer. So 1 times 3.16 is 3.16, and then 10 to the 8th times 10 to the minus 12th is 10 to the minus 4. So that would be the corresponding sound intensity level associated with 85 decibels. So those are how you go either direction. And just checking to see, I want to see if, okay. The question is, if you have two sound sources, how do you add them together? So add sound intensity. Sound intensity is not decibels. So if you have two, say if you have two sources, and those two sources at a particular distance give you, let's say from source A, the sound intensity level is 2 times 10 to the minus 4 watts per meter squared, and the other source B is 1.0 times 10 to the minus 4 watts per meter squared. The total sound, so the total sound intensity is 3.0 times 10 to the minus 4. You can just add them algebraically. But if you had two sources and source A was 70 decibels and source B was 75 decibels, the decibels for A plus B does not equal 70 plus 75. So you can't add decibels. What you'd have to do is you have to convert these two to intensity levels. So you'd have to come up with a corresponding intensity. And the way you do that, again, is what we did in this previous thing. We'd have to go through this procedure. So let's just do that. So you have 70 decibels equals 10 log base 10 of I over I0. So then you get 7.5 is equal to log base 10 there. Then you take 10 to the 7.5 power, and I get 3.16 times 10 to the 7th power. And I0 is 1 times 10 to the minus 12th watts per meter squared. Decibels don't have any units, so you get the sound intensity level is going to be 3.16 times 10 to the minus 5 watts per meter squared. 10 to the 7th times 10 to the minus 12 is 10 to the minus 5. So this intensity is 3.16 times 10 to the minus 5 watts per meter squared. And you can do the same thing for 75. So let's 75 divided by 10 is 7.5. Actually, I just did 7.5. Why did I? So let me, I don't know why I wrote that down. So write down the 7.5. That's 3.6 times 10 to the minus 5. Let's do 70 now, since I apparently did 7. So what you would get, for 70, you get 7 is equal to the log base 10 of I over I0. And so you get basically 10 to the 7th power, which is, so you get 10 to the 7th power is equal to I over I0. And I is 1 times 10 to the minus 12th. So 1 times 10 to the minus 12th times 1 times 10 to the 7th is, you're going to get 1 times 10 to the minus 5th, and then you add those up and you get 4.16 times 10 to the minus 5th watts per meter squared. So that's the sound intensity level. So you add the sound intensity levels, and then you can take this and back out what the decibels are. So basically what I'm saying is don't ever add decibels together. You have to convert them to sound intensity level, add those, and then you would go backwards, excuse me. So I take this number, so that the sound intensity in decibels is going to be 10 times log base 10 of 4.16 times 10 to the minus 5 watts per meter squared divided by I0, which is 1 times 10 to the minus 12 watts per meter squared. And if you plug those in, 4.16 e to the minus 5 divided by 1 e to the minus 12, and then you take the logarithm of that, you get 7.6. So you get 10 times 7.62, which is 76.2. So the answer is, if you have two sources which at a certain distance have these levels individually, the total sound level is 76.2 decibels. Convert them to intensity, add the intensities, convert them back. Okay, so that's sound intensity. Okay, the second topic is the speed of sound in air and other, mostly in air, but sound can travel in fluids and in solids as well. Now, if we remember back to the previous chapter, when we talked about the velocity, the wave speed on a string, it was equal to the square root of the tension force divided by the mass per unit length. And that gave you the speed, wave speed. And relating it to a spring mass system, mass per unit length, mu is mass per unit length, so if I have substituted that in there, I get this. And so the top gives you a measure of the tension times the length, gives you an idea of kind of like a spring number. This is newtons times meters, which is actually it's newtons per meter for a spring constant. But the numerator is some kind of a elasticity term, and the denominator is an inertia term. So when you look at the speed of sound, you have an elastic term and you have a kind of an inertia term. The inertia, this is density. So the density is pounds or kilograms per meter cubed. And this is, the B number is equal to negative how much the pressure changes for a given change in volume. So this is V is volume. So it's a change in pressure per change in volume relative to the actual volume. So this is like percent change in volume. Change in pressure per percent change in volume. And that's kind of like a spring constant type arrangement. So ultimately, the speed of a wave, whether it's a wave on a string or whether it's a wave in terms of in the air, it's usually the square root of some elastic property divided by some inertia property. In this case, the elastic property is this, how much does the pressure change when you have a certain percent change in volume, and the inertia term is the density. Okay. Now in a solid, you've got the same kind of deal, except instead of having B in the numerator, you have this Y. And the Y is in newtons per meter squared, and that is that's Young's modulus, which we talked about in Chapter 9. Remember, there's this relationship between the stress applied to a solid and its strain. Stress is force per unit area, strain is length, change in length per length, and Y is Young's modulus. So if you look at these, so if you look at density, that's kilograms per meter cubed, and the modulus is newtons per meter squared. So I'm just taking the units for each one of these two terms of the Y, which is the Y is modulus, which has units of newtons per meter squared, and the units for rho are kilograms per meter cubed. You put those in and you simplify them, you get newtons per kilogram. And then what you can do is you can put in for newtons, you put in 1 kilogram meter per second squared. Here, when we simplified this, you have meters cubed over meters squared, and you got meters. And so the kilograms cancel out, and you get meters times meters divided by seconds times second, and you take the square root, and you get the velocity being meters per second. So what the purpose of this whole thing here was just to show you that the units do work out. So even though this is newtons per meter squared, and this is kilograms per meter cubed, the ultimate units are meters per second, which is what velocity is, whether it's the velocity of a wave or velocity of an object. Okay. This is just reminding you that looking at Hooke's law says that if you have a elastic material, then the force that you get is proportional to the displacement. Force equals K times X. And the same thing applies when you look at a stress versus strain curve. You also get a straight line. The slope of this line is this Y term, is Young's modulus. The slope of this line is the spring constant. But they're very much related in why these look similar to each other. So anyway, to review for fluids, like fluids can be gases or liquids. You have the velocity as a square root of this, what's called the bulk modulus, and the density. It ends up being an elastic property over an inertial property. And solids have a similar kind of expression, but you use Young's modulus instead. Okay. Now for air, which is the one that's most important, is we have this relationship that says the velocity at a given temperature is equal to 331 meters per second times the square root of T over 273 Kelvin. So the 273 Kelvin is the temperature at which the velocity is 331 meters per second. And to find it at a temperature other than 273 Kelvin, you just put in the actual temperature. So if it's greater than 273 Kelvin, then you have a higher speed. If it's less than 273, you have a lower. So this is the equation that you'll use to calculate the speed of sound in air at temperatures other than 273 Kelvin, which is 0 degrees C, which is 30 degrees Fahrenheit. Okay, so why is it a function of temperature? Well, because if you go back to this equation, the bulk modulus doesn't really change with temperature, but the density does. And the density changes linearly with temperature, and so you take the square root of that thing to find out the effective temperature on speed of sound. So remember, the temperature in Kelvin is equal to the temperature in degrees C plus 273. So at 0 degrees C, it's 273 Kelvin. At 20 degrees C, it's 293 degrees Kelvin. So you need to know that conversion factor. So if I was interested in the speed of sound at 20 degrees C, I would take 20 C plus 273. That would give me 293 Kelvin. So you can converting C to Kelvin is this result. To calculate the velocity or the speed of sound in air at that temperature, you take 331 times the square root of 293 over 273, and that gives you a speed of sound of 343 meters per second. So that's how you calculate speed of sound at different temperatures. You just have to reflect that. And there's also, around this temperature, there's also kind of an approximation where you add 0.6 times T. So if you don't want to take a square root, this T is in degrees C. This only works very close to 0 degrees C. If you want much hotter than this or much colder than that, then this linear approximation doesn't work. Okay, so that's it about speed of sound waves in air. Okay, the next topic is the Doppler effect. So the Doppler effect is what happens to the perceived sound, pitch of sound, when the source is moving at a different velocity than the observer. So the source is where the noise is coming from, and the observer is some person. So you can have the source moving, the observer stationary. You can have the source stationary, the observer moving, or you can have both the observer and the source moving. And so it's really the relative speed between the two objects that's important. So here's my little example. So here you have a source, and it's emitting sound waves that are going around in spherical waves at a certain frequency. And those waves go out, and this is stationary, and this is stationary, and the waves come in, and they impinge on the eardrum at a certain frequency, depending upon the wavelength of the waves. And the person hears the same frequency as the source. Now, what happens when the source is moving towards the person is that a wave is sent out, but then this person is basically running after the wave. So the next wave that's sent out is actually closer together in the air relative to the stationary ground. Now, the person here hears the same sound as up here. If it's 400 hertz here, they'd hear 400 hertz because they're moving at the same speed. And so, relatively speaking, the person here hears the same sound, but the person that's on land is seeing these waves come at them at a smaller wavelength, lambda being the wavelength, a smaller wavelength than the source is emitting. And so a smaller wavelength corresponds to a higher frequency, which means a higher pitch. So this person hears the sound as being higher. So if you have a fire truck going by you, you'll hear this pitch be higher as it's approaching, higher than the actual frequency of the source that's produced. Then what happens is after the person leaves, then the source is running away here from the observer. And so the wavelengths get stretched out. And so the wavelengths that this person's hearing the wavelengths are longer. A longer wavelength means a lower frequency. And this all comes from the wave equation that relates the speed, the frequency, and the wavelength. And because the air is not changed, the velocity, the wave speeds stay the same. So when you decrease the wavelength, the frequency goes up. When you increase the wavelength, so you can kind of think about waves coming out and they're getting smushed. That means they're close together. Higher lambda means, smaller lambda means larger frequency, so that the velocity stays the same. That's the basic idea. Now, you could have, if you're the source here and this person's in a car, then you're going to hear the same kind of thing. If this person's moving towards the source, or the source is moving towards the person, you get a higher pitch, a higher frequency. Again, if this person were running away from a stationary source, then you would hear a lower frequency. Or if they're both running towards each other, you're going to hear higher because you get both cases. And if this person's running away and this thing's moving away, then you get even lower frequency. So if the source is stationary, then the frequency is equal to the frequency of the stationary source and the velocity of the observer divided by the wavelength of the stationary signal. This is the more general expression used when the observer is moving and the source is moving and the observer is stationary. So the frequency that the observer hears is equal to the frequency that the source emits times the speed of sound plus the velocity of the observer. So this is actually the case where the observer is moving and the source is stationary. So you take the speed of sound, v is the speed of sound, v0 is the velocity, not the initial velocity, but it's the velocity of the observer divided by the speed of sound. And it's positive when you're moving towards the source. So this is positive. So if you were moving towards the source at 10 meters per second, this numerator would be greater than the denominator, and therefore the observer would hear a higher frequency than that emitted by the source. Now if it's moving away, then this would be negative. The observer's moving away, then this is negative, which makes the numerator smaller than the denominator, which makes this a fraction, and therefore the observer hears a lower frequency than that. Remember, we use the speed of sound is 331 meters per second times the square root of T in Kelvin divided by 273. So again, V0 is positive when the observer is moving towards the source, and V0 is negative when the observer is moving away from the source. Okay, so that's part A. Again, the part B. Okay, so we looked at, first case was the observer moving towards the source. The second case is when the source is moving either away or to or away from the observer. The observer is stationary. So the velocity of the observer is 0 and the velocity of the source is something else. And it turns out that the wavelength that the observer hears is the source wavelength minus this offset due to this moving. So you take the velocity of the source and divide by the frequency of the source, and that'll give you how much the waves are either compressed or expanded. So if you solve for the frequency of the observer, the frequency the observer hears is the speed of sound divided by the wavelength the observer hears, and then you plug that into there, and then you manipulate it, you get to this equation. So this is just the math. So here we find a common denominator, combine the two, take the reciprocal, this, multiply it by that, factor out the frequency of the source, so it's equal to V divided by V minus V source. Now in this case, positive V source is moving towards the person, and negative V source would be moving away from the person. So either driving this way or passing and going that way would be negative. V again is the speed of sound. This is the speed of the source, so like the siren on a car or police car. This is the frequency that's being generated. And then you can come up with this most general equation, which says the frequency that the observer hears is the frequency that's generated by the sound source, and that's equal to the speed of sound plus the velocity of the observer, and that's when the observer is, so in this case, where you have them both moving towards each other, this would be positive source velocity and positive observer velocity, because these are both going to act to increase the frequency. So if this is positive, that makes the numerator larger, and if this is positive, that makes the denominator smaller, which makes this overall thing even bigger. If you have them running away from each other, then they're both negative. That would make the negative here would make this smaller than just V by itself. And if you have a negative here, you're going to have a negative times a negative, which is positive. So this becomes larger. So this running towards the source and the source moving towards you makes it the highest possible frequency. So that's pretty much it as far as the Doppler effect is concerned. Let's do a problem. So let's say we have a stationary observer being approached by a police car at 30 meters per second. The siren, how do you spell siren? Siren, so yeah, I guess right. The siren has a frequency of 400 hertz. The temperature is 25 degrees C. What frequency does the observer hear? So we have a couple things to do. We need to calculate the speed of sound, which is 331 meters per second times the square root of t. T is going to be equal to 273 plus 25, which is 298 Kelvin. So we get 298 over 273, and we do the calculation. So 331 times the square root of 298 divided by 273, 346 meters per second. So that's V. V of the source is positive 30 meters per second because it's approaching. And F of the source is 400 hertz. So the most general form says that F of the observer is F of the source times V plus V of the source divided by V minus V of the observer. I think that's the right equation. Actually, no, it's the other way around. So what was it again? V plus V of the observer divided by V. Okay, so there you go. The V of the observer is 0 meters per second. So now we have to just plug in. So the frequency, and it should be a higher frequency because it's moving towards it. So the frequency was 400 hertz times V, which is the speed of sound, 346 meters per second plus 0. And then you have 300, I wrote down 64. I don't know why I did that. 346 meters per second. And then we subtract 30 meters per second. What that'll do is make this denominator smaller than the numerator, which will give us a fraction great. It'll be a number greater than 1, which will increase the frequency, which is what we expected. So that makes sense. So we take 400 times 346 divided by 346 minus 30. And I hear the observer hears a frequency of 438 hertz. Okay, so that's kind of an example for you. Okay, now we're going to talk about interference of sound waves. So like with any wave, you could have constructive or destructive interference. And specifically, we're talking about two sources that have the same frequency. They don't necessarily have to be of the same, they don't have to be exactly in sync to have interference, but they do have to be the same frequency. Now normally you do range it so they have the same, not only the same frequency, but that they are in sync, that they're driven by the same electrical signal. So where you have two peaks occurring at the same location, then you get constructive interference. So what I have shown here is there are two waves. There's a red wave and there's a blue wave, and when they coincide where the peaks, then you get a larger peak. So our wave becomes amplified. Where you are in a position where you have a peak and a trough at the same place, they cancel each other out, and the sum of the two is 0. So this is where you have this destructive interference. And it's all based on geometry of the distances from the two sources, how far the sources are apart, and the wavelength of the waves. And so the geometry is that if you look at a point in space, for having constructive interference, what has to happen is that the difference in these distances, R1, R2 minus R1, is equal to some multiplier, integer multiple of the wavelength. Under those cases, what happens is you get constructive interference, and at those points, you get a louder sound. Now, if you move a little bit to the side of that, where you get constructive interference, you're going to get less and less sound, and at some point, where the case that the difference in the distances from the two sources to a point in space is equal to a count integer plus a half, so 1.5, 2.5, 3.5 times the wavelength. You get destructive interference, and you get a softer sound. So it's loud, constructive interference. So theoretically, if you have two sound sources in a acoustically perfect room where you don't get echoes, you should be able to walk horizontally in front of the two speakers, and let's say you cover up one ear, so you only hear one particular point where one ear is. You should go through locations where you hear loud sound and then you hear soft or no sound at all. So that's how interference works, just like it works. There's interference associated with light waves as well as along strings. So that's what this drawing represents, is that if you went horizontally, you should hear loud and then soft and then loud and then soft. It's a little bit difficult in our situation because we have our physics room is not very acoustically good, so you get things bouncing off the walls, which create this additional noise that interferes with it. I've tried to measure it, and it's somewhat difficult, I think, because of all this extraneous noise that comes from the surroundings. So what we're going to do now is we're going to talk about standing waves, but these are standing waves in tubes. So most wind instruments, I guess really all wind instruments, can be modeled as standing air waves, standing sound waves in tubes. So kind of as a review, we looked at standing waves on a string, and so we had two supports and we had a string which was under tension. And if you just plucked this thing and let it go, it would go doo, 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 doo. But also if you provided some kind of a excitement here at the side at the frequency, the natural frequency of this, the fundamental frequency, it would also oscillate this way. So you get the constructive interference at the center and destructive interference at the end as the waves bounce back and forth. So this wave shape occurs at what we would call the fundamental frequency of this string with a certain weight and a certain tension. But you can also get standing waves to occur in other multiples of the fundamental frequency. So the other way is to have the constructive interference occur here, have destructive interference occur at here as well as the two ends. And this would give us what we would call the second harmonic. The frequency of the energy that's being put into here would be at twice the frequency that you would need at the fundamental frequency. So the second harmonic is twice the fundamental frequency. So that is the idea of a standing wave on a string. Okay, well, let's look at a specific example of a string. So again, this is the fundamental frequency. This is what we call an antinode, where we have the constructive interference and we have the nodes where we have the destructive interference, or in this case it's actually because it's restrained here. So the case of when you have two nodes, you have, well, two antinodes. This is the second harmonic. So this string vibrates this way, and here it's not moving at all, and then you get this vibration. Here's the case with three, and it turns out if you look at a sine wave, this is only half of a sine wave. If we looked at one particular instant in time, the other half would be over here. So the wavelength of the distance between the two sides that are being restrained is equal to 1/2 the wavelength of the wave that's moving back and forth on this. Now when you have n equals 2, you get a full wave. You go up to 1, back to 0, back to here. So that's a full sine wave or a full cosine wave. So in that case, the length, the distance between the two ends, is equal to the wavelength associated with this harmonic situation. Here we have 3, so we go 1 full and a half. So it's 3/2. So the length is 3/2 the wavelength associated with that. Okay. So let's assume that this distance from the two surfaces that restrain this string is 25 centimeters, which is 0.25 meters. So the question is, what is going to be the fundamental frequency which this oscillates? Well, we have this relationship to the fundamental frequency that the length is equal to 1/2 the wavelength. So that means we can calculate the wavelength by just multiplying both sides by 2. So the fundamental wavelength is 0.5 meters. Now, to be able to find the frequency, we need to know what the wave speed is. So in this case, it's given, the wave speed is given as 30 meters per second, and that would be determined by the square root of the tension divided by the mass per unit length. So we could determine that by the physical properties of the string. So once you have that, again, we're not deriving it, we're just giving it. Then you can calculate the fundamental frequency as being 30. So if you solve for V, you get V is, or frequency is V over lambda. So you get 30 over 0.5. So the fundamental frequency, which the string would vibrate, is 60 hertz. The second harmonic would be 2 times that, which would be 120 hertz. 3 times 60 is 180 hertz. So those are the actual frequencies at which you would have to excite this string to get these different types of harmonic behavior. And here's an actual picture of a string, and you can sort of see the outlines, the maximum, the minimum amplitude. And again, remember that the you can go back to these two equations, this one, and what you find out is that the fundamental frequency of a string under tension is going to be 1 over 2L, where L is the length of the string, times the square root of F over mu, where F is tension in newtons. And the mu is the mass per unit length, which mass is kilograms, length is meters. And if you multiply this out and take the square root of it, and then multiply it divided by the units of length, you end up with the units of frequency, inverse seconds. Now for the second harmonic, this is just showing you how you calculate it. V equals the square root of F over mu, but V is lambda F, so you plug that in there, you get lambda F is equal to square root of F over mu, but lambda is 2L for the fundamental frequency, so you can solve it directly for frequency. And then that's for the fundamental frequency. Because the harmonics are n multiples of the fundamental frequency, you can just take this equation, which is for the fundamental frequency, and multiply by n to get not just the initial harmonic, the fundamental by when n equals 1, but for all the other ones, which are just multiples of that fundamental frequency. Okay, so that's it about that. Okay, this is the final topic for your Monday's View and Pleasure. So the main reason for main topic in chapter 14 is standing waves in air columns. And there's two options. You can have the tube open at one end and the tube open at both ends. And different instruments have different behaviors. A flute is going to behave like a tube open at two ends, whereas a thing like a oboe is actually like a tube open at one end. And what that does is it gives us a different frequency distribution as far as the fundamental and harmonics. We'll see that later. So here is the case of a tube open at both ends. So you provide some kind of like on a trumpet, you're creating a vibration with your lips. In a reed instrument, you're creating the vibration from the reed. A flute is actually the vibration because of the air going over a hole. So you can model this tube in this manner. You've got air coming in here, which creates this energy at a certain frequency. And the wave, because it's open at both ends, the open ends are the cases of the antinodes. So the pressure can vary here at the ends, its maximum amount. So it varies the maximum here as well. So because you have the maximum variation at the ends, you have to have the node in the middle. Now with the string, we have the nodes at the end. Now, because of that, we can have one node in the middle and two antinodes at the end. And if you look at this curve, it's only a quarter of the total wave. So if I go down here and then come back up again, like that, actually it's half of the wave, okay, not a quarter of the wave. So you've got the maximum here, you go through the 0, you go to the minimum, and then you come back up. And so this will be a full wavelength. And so what we have is that the wavelength of this fundamental frequency is twice the length. So here's the length. The fundamental frequency is twice the length. So again, going back to the equation that says, velocity is equal to lambda f. If we solve for f, it's going to be equal, so if you solve for f, it's going to be equal to v over lambda. The wavelength of this sound wave is going to be equal to 2L. So you get the fundamental frequency is the speed of sound divided by 2L, which is the length of the tube. That'll give you the first harmonic. Now when you have the next option is you can have two nodes in here. So you still have your antinodes at the ends. You can have another antinode in the middle, and then two nodes here. So you get the maximum variation of pressure here, the maximum here. Here you get no variation. And if you look at this wave at 1 instant in time, it's a full wavelength. Start at the max, go to the minimum, back to the max. So in the case of the second harmonic, the wavelength is equal to the length of the tube. So instead of putting in 2L for the wavelength in the denominator here, we put in L. So the second harmonic is the speed of sound divided by the length of the tube, or twice the first harmonic. The next option is you put another node in there, so you got 1, 2, 3 nodes. So you have to have, again, antinodes at the end because it's open, and then you have 2 more antinodes here. So if you look at it, we've got 1 full and a half, so there are 3. The wavelength is going to be equal to well, yeah, you've got three halves of a wave. 3 halves of lambda equals the length of the tube, or you can solve for lambda. It's 2/3 L. Or you can do it this way, and then if you plug that in for the wavelength here, you get 3 halves. So you have 3 halves the velocity times divided by L. Again, looking at what the fundamental or first harmonic is, it's V over 2L. Here we have 3 V over 2L. So the third harmonic is 3 times the fundamental frequency. And so this kind of arrangement gives you a fundamental harmonic, first harmonic, second harmonic, third harmonic, which are just integer multiples of the first harmonic. So let's look at an example here. We have a flute that has a length of 1/2 meter. The speed of sound at about 25 degrees C is 343 meters per second. So we plug that in here, we find that the fundamental frequency is 343 meters per second divided by 2 divided by 0.5 meters. You get 343 hertz. So that's the fundamental frequency, and the second harmonic is just twice that. The third harmonic would be 3 times that. Okay, the second case is a tube open at one end. So you've got, what you have is you have the air coming in here creating this vibration. The tube is closed here, and the sound comes out this little hole. So again, we're providing energy through this mouthpiece or reed, whatever it is. But in the previous case, we had 2 open ends, so we had antinodes here and here. But at solid surfaces, you can only have a node because the surface doesn't move. So the pressure here stays the same. It varies the maximum here. So if we think about a wavelength, this is actually only a quarter of the wavelength. You have to go down there to get half the wavelength, and you have to come all the way back up again. So relative to the dimensions of the tube, the wavelength is 4 times the length of the tube. Lambda is equal to 4L. Again, using V is equal to the lambda F, solving for F, and plugging in lambda, you get the fundamental frequency is B over 4L. So this actually gives you a lower first harmonic than a tube open to both ends. Now the next case is you can have 2 nodes, just like before, one node being here, one node being there. And so what we have is we have 3/4 of a wavelength. So we'd say, what we say is that L is equal to L equals 3/4 lambda, and is that right? Yeah. So that's lambda's 4/3 L. Plug that in there, and you find out that there is no second harmonic. There's a third harmonic. It's called the third harmonic because it's 3 times the fundamental or first harmonic. And then you go to the next case, you've got 3 nodes. In that case, we have 5/4 of a wavelength is length. So you end up with the first harmonic, third harmonic, fifth harmonic, seventh harmonic. So because of the different, in fact, you don't have the second harmonics and the fourth harmonics. An instrument that is modeled after a tube with only one open end sounds different because it has different components of the harmonics. So these are the basic equations. If it's open at both ends, the nth harmonic is N times V, the speed of sound, divided by 2L, where L is the length of the tube. N can be 1, 2, 3, 4, etc. For a tube open only at one end, then the nth harmonic is N times V over 4L. And in this case, N can take only on odd integers. So that is tubes open at one or both ends, and we'll demonstrate that in class in the lab.